Hello, my name is Jim Reichard at Georgia Southern University, and this is a recording of my presentation for the 2021 Groundwater Resources Conference in Athens, Georgia. Let me share my screen and we'll get started. The title of my talk is Saltwater Intrusion and Structural Controls Within the Groundwater System on St. Catharines Island. I'm going to first give a very broad overview of the regional hydrogeology, and then I'll share some of the results from our nearly 10-year investigation on St. Catharines Island. St. Catharines is a bare island located along the Atlantic coastal plain in Georgia. Here, the most significant aquifer is the Floridan aquifer system, which is a series of highly conductive Eocene and Oligocene age carbonate units that receive most of the recharge here at the outcrop belt, where vertical gradients are downwards, and most of the discharge in this system occurs along the marine environment where vertical gradients had historically been upwards. This is a very simplified USGS cross-section through the Georgia coast, showing the three main permeable zones in the Floridan system: Fernandina, the Lower Floridan, and the Upper Floridan. The classic units that lie above the upper confining unit are collectively referred to as the surficial aquifer system. The principal water supply for the entire region is the Upper Floridan, and prior to major pumping withdrawals, we had positive artesian pressure up and down the coast. Here's a potentiometric map from the USGS showing the conditions in Upper Floridan prior to major pumping withdrawals in 1880. Blue represents all the areas in which we had free-flowing artesian conditions. Here's the USGS potentiometric map showing 1986 conditions, and we see there's been the development of a very large cone of depression due to major industrial and municipal withdrawals. Within the cone of depression, vertical gradients have been reversed, so we've greatly reduced the area of free-flowing artesian wells. Due to this loss of artesian pressure, modern seawater has been intruding laterally at Hilton Head. This breach at Hilton Head is formed. Here's the saltwater is intruding through a breach at Hilton Head through the upper confining unit. It formed during the low sea level stands of the Pleistocene when coastal rivers were actively incising through the sedimentary section. Prior to the modern pumping withdrawals, when we had artesian pressure above landscape, this breach was actually a discharge point for the Floridan aquifer. But now it's an entry point for saltwater due to the depressurization. In addition to the lateral saltwater intrusion that's occurring at Hilton Head, we have vertical saltwater issues that are taking place at a much smaller drawdown cone at Brunswick. This is a USGS map showing the two main pumping centers in the Brunswick Peninsula, along with chloride concentrations in the Upper Floridan. Based on the relationship between the plume geometry and the location of these pumping centers, the USGS has interpreted that there are high-angle faults or fracture zones that is allowing hypersaline water to move up from depth and into the pumping horizon of the Upper Floridan. This is a section from the USGS from St. Mary's up north towards South Carolina and Hilton Head, showing the carbonate units of the Floridan system. At Brunswick, the USGS has determined, based on geochemical and isotopic data, that the source of the saltwater is the Fernandina permeable zone. Now, for this to occur, that means we must have some type of vertical conduit, a fault, or fracture, or a solution collapse feature that's over 2,000 feet in length. Our working hypothesis has been, because of this length, that this feature is probably related to reactivated basement faults deep beneath the coastal plain. Take a quick look at the basement structure. This is a structure contour map of the basement that the USGS generated during the 70s and 80s as part of a large series of investigations in the cause of the Charleston earthquake of 1886. What I want to draw your attention to is this area of the Georgia Bight, where our coastal plain sedimentary sequence is draped over the basement where there's considerable relief. This is another USGS section from that same series of studies. This goes from Georgia down through the tip of the Florida Peninsula, showing complex basement faulting beneath the coastal plain. Again, our hypothesis is these faults, which are associated with opening up the Atlantic 140 million years ago, have probably been reactivated at various times in geologic past and have propagated up through the coastal plain, creating permeable pathways for the movement of groundwater. So this brings us finally to our study here on St. Catharines Island. This is a LiDAR map of St. Catharines in which I've outlined the Pleistocene core. and we have plotted 2 traverses. We have a east-west traverse in a surficial aquifer system. We have 6 wells for that. We also have a south to north traverse in the Upper Floridan. These are 4 wells that the island uses for water production, water supply. When we first started working on St. Catherine's Island, we noticed on old topographic maps like this is from 1954, that there's a linear alignment of freshwater ponds and wetlands on the island. We also uncovered written accounts from the colonial period that indicated that these freshwater ponds and wetlands were spring-fed, artesian spring-fed. My colleague Kelly Vance began doing ground-penetrating radar surveys using the extensive road network on the island. And this is an example of one of the sag structures Kelly found several meters below land surface. Shows up quite distinctly on the GPR. Based on these sag structures, we developed this conceptual model whereby during periods when we had vertical upwards gradients in the Floridan system, groundwater would have moved upwards along joints and fractures, eventually forming solution cavities. Some of these cavities would have been large enough over time to collapse, forming the sag structures that we find at the surface. So based on our model is that prior to modern pumping withdrawals, when we had positive artesian pressure, these solution conduits would have acted as places where groundwater was discharged to the surface, forming springs and wetlands. Today, with the loss of artesian pressure and the potentiometric surface below land surface, groundwater is no longer discharging through these conduits, but now these collapse features could act as an avenue for water to migrate downwards into the Floridan aquifer system. To give you an idea of what one of these collapse features may look like, here's a feature that we investigated that opened up in 2010. This is in Statesboro. This is 70 miles from the coast. Here the collapse started in the Floridan aquifer, Upper Floridan, and then propagated upwards 400 through 400 feet of clastic materials to reach the surface. We believe that this type of mechanism is one of the primary ways in which groundwater discharged from the Floridan to the surface along the coast. Now I'll share some of the results from our study in St. Catherine's from the Floridan Traverse. On the right, this is a 1997 potentiometric map from the USGS, and I've outlined the St. Catherine's Island and some groundwater flow paths. What I want to point out here is that beneath the island, groundwater in the Upper Floridan flows along a south to north flow path into the Kona Depression. Okay, so our traverse in the Upper Floridan is lined up right along a groundwater flow path into the Kona Depression. We've been collecting both field and chemistry data from the surficial and the Floridan aquifer since 2011, so we have a 9-year data set. We also have high resolution data from data loggers that have been recording temperature, hydraulic head, and electrical conductivity for the surficial wells. Here is the average groundwater chemistry from our surficial and Upper Floridan wells plotted on a Piper or ternary diagram. I want to point out that the Floridan wells are shown in blue triangles and the surficial wells are in black crosses. We can see that the Floridan water is a calcium, magnesium, bicarbonate, sulfate type water, whereas the surficial water is a strong sodium chloride type water with ion proportions very similar to that of modern seawater, which is shown by red. I also want to point out that our traverse through the Upper Floridan, the south to north groundwater flow path, falls along the mixing line, which is dominated mostly by changes in the anion chemistry. Here's our Floridan traverse from south to north. There's a cross section through that. These are our wells that we're using. And what we see, of course, is the potentiometric surface as it declines into the Kona Depression beneath St. Catherine's Island. So there's our south to north groundwater flow path. What's interesting is we've consistently found along our traverse here decreasing chloride concentrations along this groundwater flow path. Now, since chloride's conservative, one explanation for this would be dilution in mixing, vertical mixing from water from the surficial aquifer. But the problem with that is we can discard this possibility because the chloride concentration of the surficial is much higher than than the Upper Floridan. So if there was vertical mixing taking place, we'd be seeing increasing chloride along the traverse, not decreasing. So the other possibility, other explanation, is we have some high chloride source entering the aquifer on the upgradient side of St. Catharines and then undergoing dilution along the flow path. One possibility for this would be we would have modern seawater coming in through a breach in Sapelo Sound, similar to the breach in the Aquitard that's taking place in Hilton Head Island. Because the chemistry of modern seawater is well known, we can test this hypothesis quite easily. The source for this higher chloride concentration should plot on the upgradient side of our mixing line here. We can rule out modern seawater because it plots over here. It's not on the upgradient side. So it is not modern seawater that's coming into the system. What does plot on the upgradient side of our mixing line are samples from the Lower Floridan collected by Fred Falls and colleagues at the USGS. So it appears, based on this evidence, that it's the Lower Floridan is the source of our higher chloride waters coming into the Upper Floridan at St. Catharines. So in 2014, we published a paper that provided evidence support the presence of some type of vertical conduit on the upgradient side of St. Catharines, similar to what happened at Brunswick, that's allowing water from the Lower Floridan to move up into St. Catharines and then laterally underneath the island and into the Kona Depression. We believe that features like this are again related to reactivated basement faulting, and it may be more common than previously thought along the coastal plain. Now I'll share some of the results from our surficial wells. Again, we have a series of 6 wells in east-west transect across the island. There's the wells plotted on a LiDAR topographic map. We initially installed 4 wells, with well 1 on the crest of the topographic high and well 4 on the marsh side of the island. 2 years later, we installed wells 5 and 6, thereby completing our traverse across the island. These wells range in depth from 20 to 25 feet below land surface, and are instrumented with data loggers. Here are our ion results from 2011 through 2017. We have total dissolved solids. Each one of these is for one of the wells in our traverse. We have TDS, magnesium, calcium, sulfate, and chloride. What I want to point out here are the salinity spikes that we see consistently occurring in our most downgradient well 4. Okay? And we suspected that these were tidally driven. We also have our high resolution 12-hour temporal data from the data loggers. And what we see here is temperature, specific conductivity, and hydraulic head and precipitation. What I want to point out here is that our high resolution conductivity curve from our most downgradient well, again, shows significant increases in spikes in salinity. And again, we suspected that this is due to spring tides driving saltwater into the system. To give you an idea what this looks like, here's large spring tide events occurred back in 2015, flooding out the causeway leading out to Tybee Island. So what I did, I went to NOAA's database and I recorded the maximum high tide above mean high tide for every month of our study. So I looked again for the largest high tide event over mean high tide for every month in our study. And then I plotted those data on our conductivity curve for the well that's showing the saltwater intrusion events. Here's a closer look at that without all the other plots. So all the tide events that were 2 feet to 2.5 feet above mean high tide are in green, 2.5 to 3 are in gold, and those above 3 feet above mean high tide are in magenta. Clearly, what we're seeing here is spring tides or unusually large tide events is driving pulses of saltwater into the surficial aquifer in St. Catharines Island. If we go back to our previous plot, I want to point out that we don't see this in all the wells, and we don't see it even on the oceanside well. We're only seeing it around well 4 on the marsh side of the island. So this tells us that there must be some type of permeable pathway that's allowing saline water preferentially intrude in the surficial system at this well, but not the others. Our working hypothesis is that around well 4 is that we have a solution collapse feature or some type of fault, some type of permeable pathway that's preferentially allowing water to enter the system there. To test this hypothesis, We, in 2016, we installed 2 additional traverses, 2018 rather. We installed 2 additional traverses with a tractor-mounted geoprobe. So there's our original traverse. Here's our network, our 18-well network. There's the original well that showed the spikes in salinity. And here's our 2 wells, our other 2 traverses, a northern traverse, middle traverse, and a southern traverse. On the right are high-resolution specific conductivity data from the data loggers for the northern traverse, middle traverse, and southern traverse. If we go back to our original well, what we're seeing again, here's the conductivity profile for that in black. We're again seeing tidally driven pulses of saltwater intruding into the system. What's also interesting is that we found another well in the southern traverse, S4, that's also responding to these tidal events. So we have 2 wells of interest. What we did next was we did ground penetrating radar and electrical resistivity profiling to investigate the subsurface vicinity of these 2 wells. My colleagues Kelly Vance and Jackie Kelly generated these plots. And so near our original well, what we found, Kelly found a nice sag structure, about 8 to 12 meters below land surface, which also showed up well in the high resistivity layer in the ER data. So it looks like we have a solution collapse feature that's responsible for the saltwater intruding into the system there. At our site in the southern traverse, we ran 2 transects with electrical resistivity, and what we see from the ground penetrating radar is a lot of small faulting, offsets in the subsurface, and what we also see what appear to be faults, it's showing up through the high resistivity layer in the ER data. So we believe that this site is fault controlled. I also want to quickly mention that we did install a vertical nest at 6 sites. So we have a 45-foot well, deep wells at 6 sites. So we have a 25-foot well along with a 45-foot well. So we can look at track the vertical movement of saltwater in the system at these locations. And real quick, here's all our chemistry. We did end up adding some other Floridan production wells to this, so we have a better defined mixing line. And here are our shallow surficial wells in black, and our deep surficial wells, the 45-foot deep wells, are in red. Again, we're seeing a well-defined mixing line in the Upper Floridan, and we also have a mixing line in the surficial system, with one end member being having sodium chloride rich waters with a seawater signature, and the other end member would be more of a pure calcium carbonate. So the hydrogeology here is more complex than we realized initially, and we're still trying to unravel that. So to try to tie this all together, our team has found that we have some type of vertical conduit. It's either a solution collapse or a fault on the upgradient side of St. Catharines that's allowing saltwater intrusion into the Upper Floridan. We think it's similar to what's happening in Brunswick. Our team has also used electrical resistivity and ground penetrating radar, and has identified sag structures and faulting that's allowing saltwater to intrude at specific locations in the island. We believe our working hypothesis is that these features that we're finding in the surficial system in St. Catharines, we think there's probably related to the same structural feature that's allowing saltwater intrusion from the Lower Floridan into the Upper Floridan. And again, we believe all of this is likely related to reactivated basement faulting associated with the Mesozoic faults in this opening up in the Atlantic. Where we're going with now with this is that we're considering that it's possible that the fault that USGS has identified in Brunswick may actually extend up through St. Catharines and be part of the same structural features that we're finding on St. Catharines. So what we're doing now is trying to find other places along this structural trend where we may have sag structures and faulting and increases in saltwater intrusion. And an intriguing spot is in the northern end of the island in the sag structure that Kelly has already identified by GPR, and it's a drainage head. And an old topographic map, this drainage begins at this sink. So this is actually a sinkhole. And again, he's already identified it as the sag structure. We have yet to do any electrical resistivity, but we haven't put in a well there. We haven't got any results yet to share with you. So to sum up, I know I'm probably running past my 20 minutes. Our chemistry data indicate both shallow and deep groundwater in coastal Georgia moves along vertical pathways related to reactivated basement faults and solution collapse features. Within the Savannah-Kona Depression, these pathways have the potential to accelerate saltwater intrusion in both the Upper Floridan and the surficial aquifer. I know that I'm not sure how we're going to be doing questions, but if we don't have the opportunity to ask questions during the session, please feel free to email me at Georgia Southern with that address. Okay. With that, I will stop my presentation and we'll look forward to the next one.